All right, welcome back, everybody. These are the notes I promised you in regards to chords that me and Joey introduced to you a few moments ago. But the objective for the day is to be able to identify and use properties of chords. So again, the definition of a chord that my cat kind of introduced to you, it is a line segment with both endpoints on the circle. So for instance, if I have an endpoint here, and an endpoint over here, and the line segment between them, that creates a chord. Now a chord's going to have a couple parts associated with it. One of the parts is what Joey was showing you, a portion of the circle called an arc. Again, this right here is the intercepted arc. I'm not sure why they call it intercepted, but that's what they call it. Intercepted arc. Again, it's kind of created by that chord. Something else associated with this that we'll be looking at over the next several days is, again, if I have the center point here, it also has an associated central angle with it. So this is the central angle. So we'll be looking at the green chord, different properties about it, and we'll also be looking at the pink intercepted arc, and then also the blue central angle. We'll be studying those over the next several days. So that's what a chord is, and the parts associated with it. So we're going to look at three theorems about these chords today. The first one I kind of illustrated to you on my kitchen floor, and it is that congruent chords make congruent arcs. And I'm going to add to that, I should have added it in the introductory video, and congruent central angles. So down here it's illustrated with these two congruent circles right here. Again, if I have this chord here congruent to this chord here, it's going to create not only intercepted arcs that are congruent, so this arc would be congruent to this arc, also the central angles are going to be congruent as well. So this is going to be congruent to that right there. So it can happen in two congruent circles, or it could just happen in one big circle. If I change that to that, and go like this. Stop like auto-focusing or whatever it's doing. All right, so if I have one big circle, it also works in that. So if I have a big circle like this, and I draw in my congruent arcs like this, so that arc's congruent to this arc over here. So again, if they're the same length, that means these arcs here are going to be the same measure. And then also the central angles are also going to be congruent. Do those in purple. So if that's my center, that angle will be congruent to that angle right there. So it can happen in two congruent circles or in one circle itself. So that's one theorem. Congruent chords make congruent arcs and congruent central angles. The other one we looked at, I did illustrate on the kitchen floor, and that was that congruent chords are always equidistant from the center. So down here I have CD. This chord CD is congruent to AB. So if that's the case, that means that CD and AB must be equidistant from the center, which in this case is point O. So they're always going to be the same distance as long as those two chords are congruent. The converse is also true. If I know that CD and AB are equidistant from the center, that means they have to be congruent to one another. So the converse is also true. So congruent chords make congruent arcs, they make congruent central angles, and they're also equidistant from the center. So all of that is revolving around two congruent chords. There's another theorem which I covered on the kitchen floor, and that dealt with a single chord, and when I intersect that with a radius. So a perpendicular radius bisects the chord. It actually bisects three things. Bisects the chord itself, bisects the chord, bisects the arc, and the central angle, which I did not mention in the introductory video. So again, what that's going to look like in pictures. So if I have a chord again, kind of like that, and then I take a radius and I make it perpendicular to that chord. So again, it has to hit it at a right angle like that. So if that's the case, what this is saying is that the chord is bisected. It also says that the arc is bisected. And not only that, is the central angle is also going to be congruent. So the central angle is right here. That means this piece over here is going to be congruent to that one right there. So it's going to bisect three things: the chord, the arc, and the central angle. And we'll have problems that kind of use those properties. So again, the theorems go like this: congruent chords cut congruent arcs and congruent central angles. Congruent chords are also going to be equidistant from the center. And then finally, if a radius is perpendicular to a chord, three things are bisected: the chord, the arc, and the central angle. So let's see if we can use those properties. All right, so number one here is, I notice that I have two congruent chords here and here. So that means the arcs here and here are going to be congruent. So now if this arc is x, that means this arc over here must also be x. So now I notice that I have all the arcs of a circle. Well, all the arcs of a circle go 360 degrees around. So basically, to figure this one out, I would do the x plus 64 would equal 360. So that would be 2x. Then I subtract the 64 from both sides. Just like that. And then I do 360 minus 64. 360 minus 64, 296. Then I divide that by 2. I get 148. So x would equal 148. So I use congruent chords to get those congruent arcs there. Here I have congruent chords again, which means I have congruent arcs as well, here and here. So if this arc is 116, that means this arc is 116. Then I notice that I have a central angle making that arc. Central angles and their arcs that they make are always the same. That's how they get their measures, from the central angle. So if this arc is 116 degrees, that means that central angle also has to be 116 degrees. Over here, I notice that both of these chords are 4 units long, which means they are congruent. That means the arcs that they make are congruent. So that means this arc has to be the same as this arc. So if this one's 82, that means this one's 82. All right, down here, I have circle P with a radius of 13. So I know the radius is 13. RS is 24. That's this chord right here. Find each measure. And how big RT is? Well, if RS is 24 and this is perpendicular to it, remember it's going to be cutting it into equal parts. So that means each of these parts has to be 12. PT, that's going to be a little bit harder here. All right, so to figure that one out, I'm going to use little Pythagorean theorem to figure that one out, I think. So radius is 13 RS. So the radius is 13. So QP is 13. See if I can use that to help me. Draw this chord in here to make a right triangle so I can see if I can use Pythagorean theorem. So this side is 12 right here. I know this radius is 13, but I don't know what this is. And that's what they want me to find. But I do know that this would be what? 13 minus x? And so we're going to figure out how big that is. So I can't use Pythagorean theorem there because I have two unknowns. Ah, I see what I can do. I can use this radius right here, PS. PS is going to be a radius, and I know a radius is 13, so that's going to be 13. So now I know two sides. So as soon as I know two sides, I know I can use Pythagorean theorem. This side was 12 right here, so my right angle's right there. So the leg that I'm looking for is x. This other leg is 12. Hypotenuse is a radius, which is 13. So to figure this one out, it's going to be x squared plus 12 squared equals 13 squared. Well, that's a Pythagorean triple, 5, 12, 13. So that means x is equal to 5. Again, if you don't know your Pythagorean triples, just use Pythagorean theorem to figure that out. TQ then, again, since I know that x is equal to 5, I can figure out what TQ is by doing 13 minus 5, and 13 minus 5 is equal to 8. So TQ is equal to 8. That's how I'd figure that out. Down here, different one. Here I know that the diameter is 12, so that's BE. CD is 8, that's that chord right there. And then the measure of arc CD is 90. So that's this arc measure right here. So what's the measure of arc DE? Well, since this radius is perpendicular to the chord, remember that the chord's broken into two equal parts, and so is the arc. So that means arc DE has to be half of 90 degrees, which is 45. So this would be 45 degrees. FD, that's what this distance right here. Well, if the diameter is 12, radius would be 6. CD is 8. Oh, FD, again, would have to be broken into two equal parts, so that would be 4 and 4. So it means FD is equal to 4. And then lastly, AF, which again, I'm probably going to make a right triangle and use Pythagorean theorem. I know this is 4. I know a radius is 6. So this is 4, a radius is 6. So now I can figure out what that missing side is. We'll call it x. So again, it's leg squared plus leg squared equals hypotenuse squared. And so that's x squared plus 16 is equal to 36. So that means x squared is equal to 20. Square root both sides. 4 times 5 is 20. Square root of 4 is 2. So I get 2 root 5. That's how far it is from A to F. So we have more practice problems down here and on the next page of using those properties here and here. So again, you're using the properties for these problems here. Lots of problems for you to work on. Application problem here. Answers to which are all on the last page. So as you work through those, make sure you go and check your answers to make sure you're doing it correctly. So again, in closure, basically, what you'll be looking at is number 1, congruent chords do a lot of things. Again, they make congruent arcs. They make congruent central angles. They're equidistant from the center. And then the second thing we looked at is when a radius is perpendicular to a chord. Again, basically a bunch of things are bisected. Bisected items. Bisected items are the chord is bisected, the arc is bisected, and the central angle is also bisected. So again, I'd work through the rest of the notes, check my answers using all these properties here. Then I have a smaller assignment because there are so many problems in the notes. Again, as usual, you can stop in my office hours, which I posted on updates when they are. Then also, you can email me with any questions, and typically I can help you through that as well. So I'll be looking forward to hearing your questions because this stuff can get a little complicated. Remember, Pythagorean theorem can usually bail you out a lot of the times, so keep that in the back of your mind. All right, I look forward to hearing from you.